Welcome back, everyone. I want to start by drawing your attention to something I put on the board, and I just want to put it there and say it now. I'm going to say we're going to test on the 20th or 21st for you guys, which is the last day of the semester. Okay, so we're starting a unit. We got 3 weeks. We'll get to what we can, and we're going to test on the last day of the semester. So just be aware of that, because I'm sure I am not the only class you will be testing in on January 20th or 21st. So just kind of keep up with this, and hopefully it shouldn't be too bad. This unit is on work, energy, power. We're going to start by kind of introducing all of those ideas today, and that's what that sheet that I asked you to pick up on the way in is going to kind of hopefully do a decent job of this. Whatever we don't, we're going to go through a bunch of this packet. Whatever we don't finish today is going to be your virtual day assignment for tomorrow. So we will get to, I'm going to purposely skip certain things, but that's how we're going to kind of introduce this unit. So those are kind of the 3 major topics. Power is a very, very, very small part of this unit. When we talk about power, it's really just, all we're going to do is take the amount of work and divide it by time. So it's pretty straightforward in terms of calculations. Energy is where we're going to spend most of our time, but where does that energy go, or where does it come from? That's the work piece, so that's where we're going to start with. So when we talk about work is defined as, or maybe defined isn't the best way to say it, but work occurs maybe when we expend, right? We expend try that over. We expend energy to do, and I'm going to put in quotes, something. And that something is meant to be like that because I can go through and I can spend a lot of energy and push really, really hard against the board or the wall, but I didn't really accomplish anything, right? I didn't do something. I pushed, but nothing happened. So that's what we're talking about when we talk about that idea of we have to expend energy to do something. There's a very generic equation for work that we're going to use. So work is equal to, plus or minus, I know you can't see it yet, is equal to plus or minus some parallel force. That's mathematical. I'm trying to use the mathematical symbol for parallel compared to like perpendicular, right? I don't want, not perpendicular, but parallel. Okay, so it's a parallel force times delta x. Okay, so the W, the variable W, stands for work, and I'm going to put in parentheses the units that we use to define work is a joule, or we could just use a capital J. It's plus or minus, and I'll talk about how we determine whether it's plus or minus at the bottom of the sheet. This F is some force that's parallel to the displacement. So we kind of generically call it a parallel force, and all forces are measured in newtons, but a parallel force isn't a thing. You know, we had a normal force, we had a gravitational force, we had an applied force, we had a force of friction. That's not what I'm saying when I say a parallel force. I'm not calling the force by name a parallel force. The idea is the force is parallel to the displacement. Okay, it's parallel to the displacement. And that's really, when we talk about this delta x, this is, I write delta x, but this could be delta y. So we're going to talk about 4 different forces in this equation. and we'll have kind of special equations for each one. It's just a modified version of this. But when we talk about the force, we write the displacement that's parallel to it. So if we're talking about, like, for example, gravity, if I drop this pen, gravity is going to be in the y direction. This would be force of gravity times delta y. If I push this chair along the floor, applied force times the displacement in the y direction. I'm sorry, times displacement in the x, because the x is parallel to my applied force. When I drop this pen, the y is parallel to my gravitational force. So we change this displacement to be parallel to whatever force we're looking at. Okay, so that's how we can kind of approach this. So an impulse is a force acting over some amount of time in order to cause a change in momentum. On the other hand, work is a force. Work is a force acting over some amount of displacement to cause a change in energy. Oops. I want to remind you of something quick. Displacement is different from distance. Okay? Distance traveled. If I start here, I go 1, 2, 3, 4, 5, 6. Actually, I should have probably gone 1, 2, 3, 1, 2, 3. That's probably how I should have done. Distance traveled, I walked 6 steps. Distance traveled is 6. Displacement and distance are different. Displacement is how far am I from where I started. So I walked 6 steps, my distance was 6. However, how far am I from where I started? My displacement is 0. I'm back to where I started. So when we talk about displacement, it's how far are we from my starting point. So going back to the example of me pushing against the board, I was applying some type of force, but the board didn't move or the wall didn't move. Therefore, my displacement was 0. Therefore, I did 0 work when I was pushing against that wall. I expended energy, but I didn't do any work. Now, if we keep in mind the idea of displacement is how far from where you started, when we think of our traditional workout exercises, like you go to the fitness center and you go work out, if you kind of look at each one from a physics standpoint, most of those have a displacement of 0. Right? If you're going to go weightlift, you're going to grab the bar, you're going to push it up, and you're going to grab it, you're going to bench press, and you're going to put it right back where it started. Your displacement was 0. You're going to do a set of squats right back to where it started. You get on an elliptical, you didn't actually move anywhere. Treadmill, same. You're going to go home, you're going to run, you're going to leave your house, and you're going to go for a big run, and you come back to right where you were. Technically, you did 0 work in terms of physics-related definition in those activities. Not saying you didn't expend energy, not saying you didn't apply some forces, but in terms of total work done, that's the idea of displacement, is how far are you from where you started. Okay, so this energy idea, we're gaining or losing energy. And we often talk about putting energy into the system or removing energy from the system. And when we talk about energy, there's 3 types of energies that I kind of want to introduce to you today. So one type of energy that we talk about in 9th grade physical science, I know you talked about, is kinetic energy. Okay, so kinetic energy, we use, I use, let me rephrase that, the letters KE, capital K, capital E, to represent kinetic energy. That's my variable of kinetic energy. If you talk to someone from traditional physics or AP physics, I believe they just use the letter K. Okay, but that's what we're going to use. So the equation for kinetic energy, KE, is equal to 1/2 mv squared, where kinetic energy is measured in units of joules. M is mass, measured in kilograms, and V is velocity, measured in meters per second. I often will refer to One of the big things in this unit is identifying what type of energies exist. So we're do work to change or add or remove energy. We can add kinetic energy or kinetic energy can be removed from the system is often how we refer to it. So identifying whether certain types of energy exist is going to be important, and I kind of talk about the questions you want to ask. So the question that we ask ourselves for kinetic energy is it moving? And if the answer to that question is yes, it has kinetic energy. If the answer to that question is no, then it doesn't have kinetic energy. Because kinetic energy is 1/2 times the mass times velocity squared. I don't have to ask the question, does an object have mass? Because anything that is made up of matter, atoms, and takes up space, has some volume, has mass. So everything has mass. So the question I really have to ask, is it moving? If the velocity is 0, 0 squared is 0 times m is 0 times 1/2 0. There is no kinetic energy if it's not moving. So that's the quick, easy question. Is it moving? The answer is no, no kinetic energy. The answer is yes, kinetic energy. That's one type of energy that could be added or removed to the system. The next type of energy, and now these three energies I'm introducing today, we aren't really going to deal with today. I just want to introduce them so you've heard them. So when we come back on Thursday, we can then kind of build on this idea. The second one is something called gravitational potential energy. Now, in 9th grade physical science, you probably simply called it potential energy. The variables we use are PE subscript G. PE subscript G. So potential energy due to gravity, gravitational potential energy. Now in 9th grade, that was the only type of potential energy you dealt with, so therefore why differentiate it between, there's a different type of potential energy we're going to use, that's why we're going to specify as PEG. So for PEG, potential energy in general is stored energy. So anytime we have potential energy, the kind of the classic definition for anything that's potential is the ability to do work. So it's the ability for gravity to do work. If I take this pen and I raise it up, I'm giving this pen potential energy. Has the ability to do some type of work if I let it go, by raising it, by giving it height. Okay, so our equation for potential gravitational energy is PEG subscript G is equal to M times G times H. PEG, still measured in joules. M, still mass, measured in kilograms. Gravitational acceleration is measured in meters per second squared. And then H represents height, which we measure in meters. So the question we ask ourselves to determine whether there's gravitational potential energy is there a height? That's the question we ask. And if the answer is yes, then it has gravitational potential energy. If the answer is no, then it doesn't have gravitational potential energy. Now you might say, well, height based on what? Great question. If we say, does this, it's a racquetball cut in half to make up what we call popper. Does this racquetball have a height? Well, based on the floor, yeah. Based on my hand, yeah. Based on this hand, now, we'd say no. However, if we say, does this thing have a height compared to the floor, then the answer is yeah again. So height is relative. That's the point I'm trying to make. It's relative. We have to define it, and once we define that height, we just kind of go with it. So if I'm going to take something and I'm going to end up dropping it and it's going to go a certain distance, we often will define the lowest point that that object's going to go to have a height of 0. So if I'm going to drop this and it's going to hit the table, then it makes sense to define my table to have a height of 0. However, if I'm going to drop it and let it go to the floor, then that makes more sense. Any location is fine to have a height of 0. I could define right where I'm holding it in my hand to have a height of 0, but then when it's here, now it has a negative height. And more than, we're actually going to be looking more for, is there a change in height than is there a height? Because if I drop it from here to here, I'm looking for what is this change, and it doesn't matter whether this was 0, whether this was 0, or this was 0, the change in that height is going to be the same. So the idea for gravitational potential energy, is there a height? For the last type of energy is, we call it elastic potential energy. So it's a type of potential energy, so we're going to use PE, then we're going to go subscript E for our variable. Now, we use PE for potential energy. Traditional in AP physics, they use the letter U, capital U. I'm not really sure why, but that's what the textbook that they have uses. So it's UG and UE. But when we talk about elastic potential energy, we're talking about things that are elastic in nature, like a rubber band, like a spring, like a bungee cord. So that's kind of what we're thinking about when we talk about that. So PEE is equal to 1/2 times this thing called K times X squared. PEE, still measured in joules. Parentheses is kind of my code for, these are the units that are associated with all of these things. And what the letter K is, K represents something called a spring constant. So in interest of time before break, I cut out a thing on forces on springs that we would introduce spring constant, but it's okay, we'll be able to do it without. So when we talk about spring constants, our units for a spring constant is newtons per meter. And really, what that's saying is how much force, newtons, does it take to move that spring a certain distance per meter. It's a measure of how stiff a spring is. The higher the K value, the higher the spring constant. So your suspension on your car is like a spring, or maybe has a spring, depends if we're talking about coil spring, shocks, or if we're talking about leaf suspension, but whatever. The idea is when you hit a bump, your car bounces. It's like a spring. Your car is heavy, therefore it has a high spring constant. This pen has a spring in it. This has a very low spring constant. If we were to put this in your car and you hit a bump, it wouldn't be very effective. In fact, as soon as you lower your car off the lift, your spring would no longer be acting as a spring. You'd be completely compressed. So the higher that K value is, the stiffer that spring is. And then last is this X, and it's an X squared. And what we do is we measure the displacement of the spring from what we refer to as the equilibrium. And that's going to be measured in meters. So, a rubber band can store elastic potential energy. So if we have our spring, rubber band, this is right now in equilibrium. Where my rubber band wants to be is in equilibrium. If I take something and I were to, this seems like a bad idea, but it's better, and I hang something from it, what happens is my rubber band stretches slightly. And what happened is, if this is the equilibrium point, however far my spring is now from here is what that X value is. Now if we use personification, the spring wants to go back to its equilibrium. Okay? So if I take this and I pull it like this, my rubber band wants to go back to that unstretched point, its equilibrium. So the further I stretch this, the more it wants to go back, the more potential elastic energy it has. Because it's how far is it stretched squared. Now, not all springs stretch. Sometimes we compress springs. So it's how far is it stretched or compressed. It kind of goes both ways. But it wants to go back to that point of equilibrium. And we can measure that, right? So if I had this and I pull it 5 centimeters, my x would be 5 centimeters. Now it has to be in meters, so we'd have to convert it, and then we would square it. But that's all a spring constant is. We typically deal with springs that follow something referred to as Hooke's law. Hooke's law is named after a scientist by the name of Robert Hooke. He is the same scientist that was credited for naming the cell. Like, he looked at cork under a microscope and said, hey, look, they're cells. They look like cells. That's that guy. And he found this relationship between force and a spring, and that if we are within a certain range, that spring behaves very consistent. But what happens is, so the idea would be, if I were to take pound, like this is where my equilibrium is. If I put 1 pound of weight on here, it'd go this far. If I put 2 pounds of weight, it would stretch in equal distance. If I put another pound, it would go again, proportional, linear. But at some point, my rubber band stops being a rubber band and acts more like a piece of string, right? It stretches to its max. So we always kind of deal within that range in a perfect kind of situation. But elastic potential energy, the ability to do work. So how much work can that spring potentially do is really what we're looking for. So when we put work into the system, we could gain or lose elastic potential energy. We could gain or lose gravitational potential energy. We could gain or lose kinetic energy. So by doing work, we can make it go faster, we can make it go slower. By adding or removing work, we could gain or lose height, we could stretch or compress a rubber band. The question that we ask for elastic potential energy is there compressed, and I'm only going to write compressed, but it could be, put in quotes, compressed, it could be a stretched spring. Now when I say spring, it could be a rubber band, it could be a bungee cord, it could be the suspension of your car, things that are spring-like in nature. So, work, force times a displacement. You need both force and a displacement in order to do work. Work adds or removes energy to the system. We'll talk about how we can determine whether it's adding or removing in just a moment. So that's the types of energies. Maybe I'll keep it there for just a moment longer. So now questions number 2 are a series of questions that I'm asking you to go and look at the work equation, the generic work equation, where work is equal to plus or minus some parallel force times the displacement. And in order for work to be done, we need both a force and we need there to be displacement. So if we take a look at question number 2, letter A, indicate whether or not the following represents an example of work. So I kind of already did this. The teacher applies a force to a wall and becomes exhausted. I push really, really hard. I go, oh, I almost pass out. I'm so tired. Did I do any work, though? Using this general equation of work, plus or minus some force times some displacement. Did I do work when I pushed against the wall? Did I apply a force? Sure did. Did the wall move? Nope. So my displacement is 0, so therefore my work done is going to be 0. So did I do work? No. Why? There was no displacement. What about if a weightlifter takes a barbell and lifts it above her head? Did she apply a force? Did the barbell move? Therefore, did she do work? Yes. Both force and displacement. Now, what if, this isn't how this question is worded, so she took her dumbbell, she went like this, What happens if she brings the dumbbell back down? And we look from here to here, did she do work then? The answer is no, because the displacement of the dumbbell from here to here would be back to that 0. A waiter carries a tray full of food across the dining room at a constant speed. Does the waiter apply a force, and does the waiter move? The answer is yes. So therefore, the waiter does work by walking across the dining room at constant speed. Constant speed is not actually important in this situation. He put some force in order to move. Shot putter launches a shot. That's the steel ball. Yes or no? Do they do work? Did the shot putter apply a force?
Yes.
Did the shot put move?
Yes.
Therefore, did work. Okay, this next section, I'm just going to tell you, work is a vector quantity. Okay, so it's not going to be choice B, it is not going to be choice D. Work is a vector quantity. And it is, so work is a vector. A plus or minus sign on a work value indicates information about whether the work adds or removes energy from the object. So that's this whole plus or minus piece. The plus or minus tells us whether we're adding work or we're removing work from the object, or often I refer to, instead of the object, I refer to it as the system. So how do you determine whether it's positive, negative, or also we could say 0? So work is work is zero when the force is not parallel to the displacement. Okay, so no work is done if the force is not parallel to the displacement. Okay, that's 0 work would be done then. An example of when a force does 0 work on an object, I'm pushing this chair, I'm applying a force. That way, I'm doing work on the chair. If we look at all the forces acting on this chair, though, there's also gravity, and gravity's pulling down. Now, if I'm moving the chair this way, it's moving in the x direction, it's not moving in the y direction, therefore the force of gravity, the force that we're talking about, is not parallel to the displacement, therefore the work done by gravity is going to be 0. There's 4 different works that we're going to look at specifically. Okay, so work is 0 if they're not parallel to one another. Work is positive when the force is in the same direction as the displacement. So work is going to be positive if it's in the same direction of the displacement. So, chair, me, applying a force that way. If I'm applying a force that way, my force, the applied force is that way. The chair is moving that way. If the force is in the same direction as the displacement, the work being done is positive, which means we're adding energy to the system. Now the opposite of that is going to be true, and I'll write that in just a second. If I'm applying a force this way, we have friction that's applying, the force of friction is this way. Chair's moving that way, friction's moving that way, those force and displacement are in opposite directions. It's going to be doing negative work, or removing energy from the system. It's possible for your applied force to be in the opposite direction. That one's a little harder to show, but if we can kind of visualize this, you get out of your car, you're in a hurry, you put your car in neutral for some reason, and you hop out of your car. And your car starts to slowly roll away. And you realize that. So you go and run in front of it, and you try to slow it down, and you push against it. The car continues to move, you're able to stop it eventually, but while the car is moving this way, you're pushing this way. You are removing energy from that system. You're doing negative work. So the idea of work being negative, work is negative when the force is in the opposite direction as the displacement. Okay, marker is going to be negative. Okay, so it's going to be negative. It's going to be negative when they go in the opposite direction. So I just put a little star there, and the reason I put that star right there is I'm going to write some stuff on the board that I would suggest you write where I put that kind of star. I'd shift it all the way left, but I couldn't really show it. Okay, so the general equation that we use for work is that there's four types of work that we deal with. We're going to talk about 4 different types today. After tomorrow, we're really only going to ever talk about 2. The 2 most common types of work that we deal with are something referred to as work in and the work done by friction. This is a subscript, this is a subscript, is what they're meant to be. So if we use this generic equation for work, if we change this parallel force to be a specific force, we get different types of work. So if we talk about work in, we're putting work into the system, what kind of force would we be doing if we're putting work into the system? Typically it's going to be an applied force. Now, plus or minus is important. So when we calculate the work being put into a system, is going to be plus or minus our applied force times delta x. This is a generic equation. This is the specific equation that we can use to determine if there's any work being put into the system. Applied force times displacement. Now you can say, well, how do I know if it's the plus or minus? Same direction as your applied force, positive. Opposite direction, negative. Work done by friction. I'm going to leave this plus or minus out for just a second. Is going to be the force of friction times the displacement. Now, how do you determine whether it's the plus or the minus? Well, you have to go through and say, is my force of friction in the same direction as my displacement? If so, it'd be positive. Or is my force of friction in the opposite direction of the displacement? Then it'd be negative. Which direction does friction always go? With the motion or against the motion of the object? against. So because friction always opposes motion, the work done by friction is always going to be minus the force of friction times displacement. This is always going to be a minus. Now, I do want to note that in both of these, this delta x could be delta y. Because I can apply a force in the y direction. Then it'd be my applied force times the delta y. Air resistance is an example of friction in the y direction. So we could substitute this as a delta y if it's moving in the y direction. Those are the two most common works that we are going to deal with after today. Today and tomorrow, we are going to talk specifically about two, and then we really don't deal with them because there's other ways we can address them. So the other two types of work that this kind of worksheet kind of works us through is there's this thing called work done by gravity, which is equal to plus or minus the force of gravity times the displacement. Now, because gravity is always acting in the y direction, we're going to say times delta y. And you'd have to choose whether it's positive work or negative work. And you can say, well, isn't gravity always down? Yeah, gravity is always pulling down. But this marker can move up or move down. So, right, that the marker is moving down, gravity is pulling down, that was positive work. But if we look on the marker on the way up, the marker was moving up, gravity was pulling you down. That would have been negative work. So there's that. The last one is something that is we barely ever use it. And this work done by the normal force is equal to plus or minus our normal force times displacement. Now, in our situation, because we don't do angles, the normal force is always straight up and down. But technically it's perpendicular to the surface, but because we don't deal with trig functions, it's always going to be straight up. Because of the idea of normal force, a normal force only exists when an object is sitting on a surface or resting on a surface or sliding across the surface or rolling across a surface. If there was ever a delta y, like we pick the thing up, there's no longer normal force. So because of the idea that as soon as there is a delta y, there is no normal force, for our purposes, that is going to be a zero value. Our normal work done by a normal force is always going to be zero. Ours. I'm not saying every situation ever in the world, but for our situations, it's always going to be zero. There's one last thing, and there's this idea of something called net work, which is really just saying if we were to sum up all of our works, right? F net is the sum of all my forces. Just the same idea. Net work is the sum of all my works. All we do is we go through and we say work in plus work done by friction plus the work done by gravity plus the work done by my normal force, and we add those all up. That gives us something called net work. We don't have to worry about x's and y's. When we talk about work, we simply add them all together. You know, we can't do that with F nets, but that's what we do when we deal with works. All right, let's look at page 2. Page 2. Page 2, question number 4. There's a couple correct answers. This is the one I really want you to know. We use the unit of joule to measure work. Now, technically, work is equal to a force times a displacement, which forces we measure in newtons. Displacement is in meters. That one actually works out too. Because of that, so does this one. And then if we did some fancy calculations, we could determine that. Okay, so technically it's A, B, C, F. I really want you to know A. That's the thing I really want. So number 5 is talking about positive versus negative work. Same direction, force and displacement, same direction, positive, opposite direction, negative. So if we have a car, number 5, a car is moving east, skids to a stop across some dry pavement. So our delta x is moving this way, and my car is moving to the right, and we're talking about the car is skidding to a stop, the force is going to be going in the opposite direction. So therefore, negative work is being done. We're removing energy from the system. A freshman stands on his toes and lifts a civics book to the top shelf of his locker. Now we are talking about in the y direction, delta y lifts the book upwards. The force is also going to be upwards. He's applying a force. Same direction, therefore, positive work. Six Flags roller coaster is lifted. Delta y is up. Force is up to get to the top of the first hill on the roller coaster called Goliath. Because these two are in the same direction, positive. A catcher, I'm going to go with this idea that the catcher pushes his mitt out. He's applying the force to push the glove out, therefore positive. Now we aren't talking about the ball hitting the mitt, that's a whole different situation. Last one, delta y, a parachutist opens the parachute and slows down. The person is going down. By opening up their parachute, they are increasing the air resistance, which is going to be up. Therefore, that parachute is doing negative work on the system, or it's removing work from the system and slowing that person down. All right. Number 6, again, I'm going to try to get through a couple of these. I'm going to get through a couple more. Whatever we don't finish is your homework for tomorrow's virtual day, but the intent was never to finish this, but. Number 6, so the idea is we're trying to determine how much work is being done by this applied force. So we are talking about the work in is equal to plus or minus the applied force times displacement. That's the equation we're going to use. It's the equation on the board because we're talking about an applied force. So this is my applied force. 100 Newton force is applied to a 15 kilogram object to move a 15 kilogram object a horizontal distance of 5 meters at a constant speed. So horizontal means that the displacement is in the x direction. It happens to move 5, and I hope we can kind of go through and say it's implied that since the force is being applied to move the object, that they're both moving to the right. So we can go through and we can say, well, the work in is going to be plus or minus. Now, is that going to be the plus or the minus? Are we adding energy to the system or removing energy? They're in the same direction, therefore there's going to be positive or negative. It's going to be positive, so it's going to be plus, and then our applied force in the free body diagram was 100 times how far did it move? It moved 5 meters, therefore the amount of work that went into the system is a positive 500 joules. The work in is positive 500 joules. A 10 Newton force is applied to a 20 Newton. A 10 Newton force is applied up, and a 20 Newton force is applied to move a 15 kilogram object at constant speed in a horizontal distance of 5. That's telling me that my delta x is equal to 5 meters, and I hope, again, it's implied that it's going in the same direction as the applied force. Now, if it's moving horizontally, how far does it move vertically? It's not, right? It's not going to move horizontally or vertically. So there's really two works being done here. There's a work in and there's a work in. Now, this has a number 1 right here, and this has a number 2, so we can call this work in 1 and work in 2. So work in 1 is plus or minus my F1 times the displacement. Now my F1 is vertical, so then we have to make sure my displacement is parallel to my force. So it's going to be delta Y. My F2 is horizontal, so it's going to be plus or minus F2 times delta X. Now, we could say, is it in the same direction or opposite direction for this one? However, the work in by this force is 0 because it's not moving vertically. For work in 2, F2 is to the right, displacement is 5 to the right, therefore this is going to be positive. We add them, they're in the same direction, times 5, this is going to be positive 100 joules worth of work. Questions on those? We're going to skip the next one. I'll kind of, so which means it's part of your homework. And I'll kind of get you going on that one. But the idea is for letter 6C, on the top of the next page. Now it's dealing with gravity. So 6C says an upward force is applied to lift a 15 kilogram object to a height of 5 meters. This is saying that my delta Y is 5 meters up. Okay, and again, I'm looking for the work in based upon that force. I'm going to skip that one. That's part of your homework that I want you to finish. In interest of time, I'm going to do one more problem. Quickly, I'm going to do one more problem. I'm going to do number 7C. Okay, that means you got to do A, B. There's 3 more on the back. When you submit this assignment on Canvas, I only need to see a picture of page number 3 and page number 4. We're using those 4 equations that I wrote on the board and you wrote on the bottom of page 1. These are going through and looking at my free body diagram and specifically talking about how much work does each thing do. It says that there's a delta X of 5 meters to the right. If it's moving to the right, that means it's not moving vertically. My delta Y is going to be 0. Work done by my normal force is plus or minus my normal force times delta Y, but because my delta Y is 0, this is 0, which means the amount of work done by my normal force is 0 joules. My applied force, my work in is plus or minus my applied force times delta X. This is moving in the X direction, therefore it's delta X. Displacement's to the right, applied force is to the right, they're in the same direction, therefore that's going to be positive. My applied force is 10. My displacement was given in the problem right here of 5. This is a positive 50 joules worth of work. Plus or minus the force of gravity times delta Y, but because my displacement is my delta Y is 0, the amount of work that gravity does in this problem is also equal to 0. 2 last pieces really quick. The work done by friction is always, according to the board, is always going to be minus the force of friction times delta X. So this is going to be minus 10 times 5. This is going to be minus 50 joules. Last piece, this will go quick, I promise, is when we talk about net work, all I'm doing for net work is I'm adding those 4 works together. This one was 0, this one was 0. So the net work is equal to positive 50 plus negative 50. Overall, there is 0 joules worth of work being put into the system. Okay, so I skipped the top one. and I skip the next two, there's 3 on the back. All of the answers to these are listed on the back. Take a picture of pages 3 and 4. I only need 3 and 4. I don't need 1 and 2. Submit that on Canvas. That is your virtual day assignment for tomorrow. Have a great day, everyone.